For this last day of notes, we're going to be taking one topic and breaking it up into 3 different sections. So for the first section, our aim is to understand the meaning of empirical formulas of compounds. So we have been looking at empirical formulas already. We just need to understand what they mean. So looking at these formulas, we should be able to answer these 2 questions. How are they different and how are they similar? We can see that they are different for one obvious reason. They have different subscripts. So for CH2O, remember these are implied ones. So we can see that we have subscripts of 1, 2, 1 on the left and 6, 12, 6 on the right. So that's how they are different. And they're similar in a couple of ways. Number one, they have the same elements. Both of these have carbon, hydrogen, and oxygen in their formula. They are also similar because the ratio of one element to another is the same. So we can see looking at the formula on the left, if we have 1 carbon, we have 1 oxygen. And we see that same ratio on the right, 6 carbon to 6 oxygen, is still a 1-to-1 ratio. So we can see that the formula on the left is actually just the formula on the right written in lowest terms. Now we have 2 formulas here. One of these is what's known as an empirical formula, and one of them is what's known as a molecular formula. So the empirical formula is the one on the bottom. It is the one in lowest terms. The molecular formula is the actual formula. So empirical is the simplest formula, the smallest whole number ratio. That can represent multiple molecular formulas because multiple molecular formulas might have the same ratio. I might have a molecular formula that is C12H24O12, and even though this is the formula of the molecule, the empirical formula is still the same, or the formula in lowest terms would still be the same for all of these. The molecular formula then is the actual formula. This is what we would actually see if we were looking at one formula unit of this molecule. The empirical formula is a way to generalize a group of molecules with the same ratio. So what we need to look at here is how we might turn one into the other, or how we might be able to identify whether something is molecular or empirical. In the case of the molecular formula, what I'm looking for is, can those subscripts be further reduced? Can I take the 12 and divide it by the lowest number? In this case, I can. So I can divide each of these subscripts by 6. And if I divide each of them by 6, I get C1H2O1. So we can see that indeed the ratio is still the same. This one, however, I cannot reduce further because if I take the lowest subscript, which is 1, and I divide each of these by 1, then I still end up with the same empirical formula. I still end up with C1H2O1. So if you can't do that anymore, you are in lowest terms, and that is the empirical formula. So take a minute and try this practice. What I'm asking you to do here is to give the empirical formula for the following molecular formulas. Pause your video, see if you can come up with the answers. So in the first one, we can see that this can be further reduced. This is not in lowest terms. So what I can do is divide each of these by the number 6. And if I do that, I get an empirical formula of CH, because each of those subscripts divided by 6 gives me a 1. And since I can further reduce it, this would be the molecular and this one the empirical. For the next one, so how we might do this is we're going to take the smallest number, because if we divide the smallest number by itself, that automatically gives us a subscript of 1. So we're going to divide all of those other numbers by the smallest number. Then the smallest number here is 2. So if I do that, what I get is C6H2, Cl2, and O1. You can see I can't reduce this any further because since I already have a 1, 1 divided by 1 just gives me 1. So this is as far as I can go in terms of the empirical formula. And then for the next one, I want to, again, take the smallest number, which is 2, and I'm going to divide each of these by 2. And when I do that, I get C3H8N. So you can see the molecular formulas on the left can all be further reduced to give me empirical formulas on the right. This section was all about being able to identify the difference between a molecular and an empirical formula, and then being able to turn a molecular formula into an empirical formula. In our next section, we're going to learn how to calculate these empirical formulas. So when we see an empirical formula, it's usually the result of some sort of laboratory analysis that has given us the information we need to calculate the ratio of one atom to another. And we're going to look at how to do that in this section. We follow a series of steps when we go through this process. And what we have to remember here, remember, I don't want you to learn things in terms of steps. I don't want you to be able to memorize a series of steps to be able to calculate something. I want you to understand what it is you're calculating. So if we're looking at the formula H2O, for example, this tells us a couple of different things. It tells us that we have 2 hydrogen atoms for every 1 oxygen atom. But remember, since the mole is just a quantity, we can also use those subscripts to give us the mole ratio of one atom to another within a compound. In other words, I also have 2 moles of hydrogen atoms for every 1 mole of oxygen atoms. So I can calculate moles and be able to determine what those subscripts are. So if you are asked to determine an empirical formula, what you're actually calculating is a mole ratio of one element to another in a compound. So you can do it that way by actually remembering what it is that you're solving for, or you can follow this series of steps. So step number 1 would be to take your given information and to convert that to moles of each atom. Step number 2, you're going to divide each number of moles by the smallest number of moles. This is similar to what we did when we were turning a molecular formula into an empirical formula. By dividing by the smallest number of moles, you're ensuring that one of those elements will have a subscript of 1 next to it. And then the third step is to multiply by the smallest number that will convert all numbers to whole numbers. This is often not necessary. This would be one of those A-level questions where you have just one more step that you have to do to be able to determine the correct answer. So a sample problem might say 0.6884 grams of lead combines with 0.2356 grams of chlorine to form a chloride of lead. Calculate the empirical formula. Remember, identify empirical formula and think about what that means. That means mole ratio. So what we want to figure out here is the mole ratio of lead to chlorine. And if we want to find the mole ratio, that means we have to first convert to moles. So this doesn't rely on repeating those steps, but you are welcome to do it that way. So if we're starting with 0.6884 grams of lead, we want to be able to convert that to moles to give us the mole ratio. So where did this number come from? That's the molar mass from the periodic table. Remember, that is the number of grams per mole for lead. And then we get 0.0033. Remember, that is moles of lead because grams have canceled. Now, if we're finding a mole ratio, we need to know how many moles of the other element we have available. So 0.2356 grams of chlorine, again, using the molar mass from the periodic table, and that is 35.45 grams of chlorine per 1 mole of chlorine. And then this gives us a total of 0.0066. If you're getting these answers wrong for number of moles of each element, make sure you're putting it into your calculator correctly. It's always the number we start with divided by the number on the bottom. And since the 1 is on the top, we can ignore the 1. Now, we've determined the number of moles of each element that we have available to us. We need to determine the mole ratio here, which means we need to figure out how many of one equals how many of the other. And in order to do that, we have to divide by the smallest number of moles, which in this case is 0.0033. We're going to divide both of those values by 0.0033. This is what gives us the ratio. So we can see that for lead, that comes out to 1 because we divided it by itself. For chlorine, that comes out to 2. Now, what do we do with these numbers? Well, the same way that subscripts represented a mole ratio when we were looking at H2O, these numbers or these mole ratios become the subscripts in the formula, which means my formula is now Pb1Cl2, or more appropriately, PbCl2. What we've determined with this whole number is the mole ratio of one element to another within this compound, based on the data given to us from lab. Now, another example would be if we are given percent composition. Now, the process here has one additional step, but it's not even something you really have to remember. Now, if we have 100% of a sample, and then we are told 50% of that is a certain element. And if we're assuming that we have 100 grams of that sample, 50% of 100 would then be 50 grams. So assuming 100 grams of sample is totally acceptable because it allows us to just put this in numbers that make sense to us. And if we do this, all we have to do is then take the value of the percentage and convert that directly into grams. Remember, we're dealing with ratios here. So if I'm talking about percent of 100 grams, as long as I'm using that 100 gram sample for each of these percents, it works out exactly the same. So all I have to do here is change the percentage symbol to a gram sample, gram unit. So 65.02% of 100 grams is 65.02 grams. Now, what I want to do at this point, since I'm determining the empirical formula, what I want to figure out is the mole ratio of one element to another, which just means I'm going through the same process I did before. I'm taking the mass and I'm dividing the mass, and you can even do it that way if you want to. You can divide mass by molar mass, and that gives you moles every time. So the molar mass of platinum from the periodic table is 195.08 grams per mole. And this comes out to, once you do the dividing, 0.33 moles of platinum. Take just a minute, pause your video, fill in the rest of these. Make sure you're able to find the molar mass from the periodic table and then to calculate the moles based on that value. So for nitrogen, 9.34 grams of nitrogen, all we did was take the percentage sign and convert it to grams. And then we divided that by the molar mass you should have just found from the periodic table. And this comes to 0.66 moles of nitrogen. For hydrogen, again, all we're doing is taking that percentage symbol and turning it to a gram unit. So dividing 2.02 by 1.01 gives me 2 moles of hydrogen. And then for chlorine, 23.63 grams of chlorine divided by 35.45 grams of chlorine gives me 0.66 moles of chlorine. We have the number of moles of each element, but we want to see how they relate to each other. So we're dividing the moles of each element by the smallest number of moles. And that, remember, just makes one of these elements automatically have a subscript of 1. And that way we know it's in lowest terms. So the lowest number in this case is 0.33. So we're dividing each of these numbers by 0.33. The number we get as a result for each of these will be the corresponding subscript. So we see that for platinum, we have a subscript of 1, for nitrogen, 2, hydrogen, 6, and chlorine, 2. So this is our empirical formula based on percent composition. This part was exactly the same that we did just a minute ago. The only difference was converting percent to grams, and all we did was just change the number. Or I'm sorry, we just changed the unit because we were assuming that we had 100 grams of sample. Now for 8.8, this is our last section for today. We have one aim, and this is to learn to calculate the molecular formula of a compound given its empirical formula and molar mass. So this goes back to the idea of how does a molecular formula relate to an empirical formula? It is a multiple of that value. So we saw when we were looking at C6H12O6, this was the molecular formula, and then we were comparing that to the empirical formula, which was CH2O. So the molecular formula is a certain number of times larger than the empirical formula. So that's the guiding factor here, is that we want to find out how many times larger the molecular formula is than the empirical formula. And we can see here that when we multiply the empirical formula by 6, we get the molecular formula. So what does that look like in terms of an actual problem? Again, you can follow these steps, but the steps just get you to the bigger picture of what are we trying to calculate. The first thing you want to be able to do is to calculate the mass of the empirical formula, which may mean you'll have to calculate the empirical formula first, like we did in the previous section. Then you want to divide the mass of the molecular formula by the mass of the empirical formula, and this just answers the question, how many times larger are we looking at? And then once we figure out how many times larger the molecular formula is than the empirical formula, then we multiply the subscripts by that answer. Similar to in the last slide, how we had to multiply CH20 by 6 to get C6H12O6. What we're figuring out in number 2 is this value. We're trying to figure out how many times larger the molecular formula is than the empirical formula. And the last step is to just carry out that multiplication to then find the molecular formula. So a sample problem might say, calculate the molecular formula. The molar mass of the molecular formula is 98.96 grams per mole. But we have to be given a series of percent composition values for this compound. We need a place to start from. There are many molecular formulas that could potentially have a molar mass of 98.96 grams per mole. We need something else to go off of. So we're given this percent composition information. This would have to be given to you. So we follow the same process we've done in previous sections. We're assuming that we have 100 grams of sample, so this percentage gets changed cleanly into grams just by changing the unit. So we end up with 71.65 grams of chlorine. The next step, again, ultimately, since we're calculating the empirical formula first, we need to turn this into a mole ratio. And remember, mass divided by molar mass gives me moles. And once I determine moles, I can find the mole ratio. So I'm dividing 71.65 by 35.45. And this gives me 2.02 moles of chlorine. This is the same thing we were doing in the last section, so this part has not changed. What will change is what we do with our final answer. The next part is the same, 24.27 grams of carbon. Again, we just turned percent into grams by assuming that we have 100 grams of sample. Now we're dividing by the molar mass to be able to convert grams to moles. Remember, grams of carbon cancel here. So we're left with 2.02 moles of carbon. And then for hydrogen, 4.07 grams hydrogen divided by the molar mass from the periodic table, which is 1.01 grams per mole. And this gives us a total number of moles of hydrogen of 4.03 moles of hydrogen. The next step in determining empirical formula, which we have to do before we can calculate molecular formula, is to divide by the smallest number of moles. And in this case, that's 2.02. Now, you can see that this is pretty close. We're close enough that we can use that value and round it up to a whole number. So we get CH2Cl. Now, remember, this is the empirical formula. So our next step after we've calculated the empirical formula is to figure out how many times larger the molecular formula is than the empirical. And we were only given the mass of the molecular formula. So what this means is we have to determine the mass of the empirical formula, and then we can figure out how many times larger the molecular formula is. So we can see here, without even really doing any math, that the molecular formula is twice the empirical formula. But you can do the math to check the numbers and make sure you're getting a whole number for yourself. So we've just figured out that now our molecular formula is twice the empirical formula. which means all we're doing is taking everything that's in the empirical formula, the subscripts, and multiplying them by 2. So our molecular formula is now C2H4Cl2. And as a check, what you can do is calculate the molar mass of this compound. And you'll find that adding up all of these elements with their associated subscripts does give you a total of just about 98.96. So our math checks out. So again, in calculating the molecular formula, we need to be given a couple pieces of information. We need to be given the molar mass of the molecular formula and the percent composition of our compound. We need to then convert percentage to grams, grams to moles, mole ratio. We need to find out how many times larger the molecular formula is than the empirical formula. And then we need to multiply everything in the empirical formula by that factor. Again, you can do this in terms of just remembering the steps, but for me, it's much more meaningful to be able to think about what am I trying to calculate. So in the empirical formula, you're calculating the mole ratio. And in the molecular formula, you're calculating how many times bigger the molar mass given is than the molar mass of the empirical formula.